Name is Rao and I'm in lab M03. This is lab 11, the following Slinky. Problem. Does the bottom of my model Slinky stay stationary just like in the video? Use the momentum principle to help answer your question. Main result. The bottom of my model Slinky does in fact stay stationary just like in the video. This is because the bottom of the Slinky didn't know it was supposed to fall until it got its signal from the top of the Slinky. Only when the metal directly above the last coil transmits the signal do you see the bottom coil with the ball start to twist and fall. So I used the video that was given to us in Web Design and I uploaded it onto Tracker. So what I did was I set the origin to the top of the Slinky right here, and I made the positive x-axis going this way. So the Slinky will fall in the negative y direction. I use the mass of the ball as 0.0635 kilograms, and let's see what happens when I click play. So if you look closely, you can see that the ball did not move very much as the Slinky was falling down. Only until the very end did the ball actually move downwards. I also used Tracker to help me find the different positions of the actual tennis ball. It's a little bit blurry because I'm zoomed in, but you can see for yourself the ball is right, there. So let's play. So you could see that the ball stayed relatively the same throughout the video until the very end, where the Slinky got very close to the ball and the ball moved much further down the y-axis than previously. So this is the Python code I used for my video. I used it from Lab 8 using the Slinky. And so I updated all the ball.mass, spring mass, and everything. I kept it as the same from the Lab 8. So what I did change was the delta t, which is 1/410, and I made it small, an integer multiple of the time interval between frames of the experiment video. I also made it while t is less than 0.18. Now to update the position of the spring in the ball, I use these two formulas right here. So I use spring for the spring position. I use spring dot position plus spring dot velocity times delta t plus 0.5 times f net spring divided by spring dot mass times delta t squared. So it's just the position formula. I derived this using the momentum principle. So yeah. So now let's take a look at the code as it's run. So this first graph right here shows the position of the ball, which is the red line. It stays stationary, and the net force is the green one. This is the force of gravity, which is negative, plus the spring force, which is positive. So you can see that even though there is a increasing net force, the position is still the same. Now this graph here shows the force of gravity and the spring potential force. Sorry, that's right here, and then the net force right here. Let's take a look at the tracker data. So here we have the spring, the position of the spring, and as you can see, it moves in a fairly linear line, curving towards the end and starting off a little bit slower towards in the beginning. Here we have the position of the ball as it moves, and you can see that in the first 8 seconds it moves only 0.06 meters downwards, which is very minimal. And then you can see here as the Slinky gets closer towards the ball, the ball moves much further down the y-axis than previously. Basically, the reason why the ball does not move downwards as you let go of the spring is even though that there's a positive or increasing net force acting on the ball, is because it takes time for the motion to travel at the speed of sound, and by the time that happens, the Slinky is already towards the bottom and the ball is moving downwards. So that is why the ball remains stationary for the while until the slinky is towards the bottom. Thank you for listening and have a great day.